Hello everyone and welcome. The topic I'm going to talk about today is a case study profiling OCP servers for holistic air cooling. I'm the one on the left here. My name is Jeffrey Sarkinen. I work as a researcher at RISE Research Institutes of Sweden at a unit focused on data centers, which is located in northern Sweden in Lulea. This work was supervised by Dr. John Summers, a research lead, and also made possible by all my colleagues there in Lulea. On the agenda today, we're going to talk about what is holistic cooling. I'm going to show the experimental setup used for the server profiling, as well as the results of the server sweet spot analysis. These results are going to be applied in a theoretical fashion to a real data center to obtain a holistic sweet spot. And finally, we're going to take a look at the effect of server inlet temperature on data center efficiency. So what is holistic cooling? In a data center, you have cooling systems and you have IT systems. The cooling systems have their control loops to maintain a desired inlet temperature to the rack, and hopefully they do that. The IT systems have fans to maintain a desired component temperature, CPU temperature for example, which in turn provides a delta T. So to ensure that these systems are in sync from a system perspective, holistic cooling needs to be used and knowledge of the other system needs to be known, as well as real-time data transfer, including fan speeds and CPU temperatures, for example, which would be provided to the cooling units from the servers. This is a chance to mention the talk coming up in the time slot after this, which will be held by my colleague Dr. John Summers, which is called BTDC, a practical demonstration of world-class efficiency, which will show holistic cooling implemented in a real data center. So now I'm going to talk about the experimental setup used, and I'll start with the server wind tunnel. This is an controlled environment to run servers, where we can control the inlet temperature, the pressure drop across the server, and the humidity. And to show how it works, we'll look at the picture on the right here. The air first enters a cooling heat exchanger, so it's cooled, and then it passes through a heater. There's a humidifier to humidify the air, and a droplet catcher, and then a fan to push the air into the inlet to the servers. Down below is another picture here which shows that we're measuring many different things in the wind tunnel. And there are also PI controllers being used to control the heater and the fan, which control the inlet temperature to the servers, as well as the pressure drop across the server. So the interesting thing here is that this is actually a small-scale version of an OCP data center. I have been in an OCP data center, the Facebook data center here in Lulea. So this picture here is provided by the Data Center Handbook, and it shows an OCP data center. The beginning here we have the cold outside air, which is cold because we're in northern Sweden in Lulea. In the wind tunnel we have a heat exchanger to cool the air. It is then mixed with the return air coming from the IT equipment. While we do not have mixing from the return air occurring, we have a heater to simulate this process. After that, the air is filtered, misted, and passes through a mist eliminator before the fans push the cold air into the cold aisle, which is also occurring here in the wind tunnel. Here's a picture of the wind tunnel. The air is moving from right to left. On the bottom picture here, I'll show you, here's where the server is located, and the picture at the top shows a close-up view when the wind tunnel is opened with the server in it. The OCP hardware we used in this experiment were Winterfeld servers, which have a built-in fan speed control interface. Now these servers usually are mounted in a rack and receive their power from a 12-volt bus bar at the back. So to be able to run one server standalone, we had to build some custom cabling shown on the picture on the left. Picture in the middle shows the external power supply used, as well as the DC power meter to monitor the 12-volt power. Here's the server ready to go in the wind tunnel, but in our experiment we actually had 3 servers and we took an average over the 3 servers for the analysis. So what can we change on the server? There's 2 things we can control. One is the workload. We use a tool called StressNG to vary the workload from 0 to 100%. The second thing is the server fan speed, which is available to do because of the built-in fan speed control interface. So we've developed a PID controller which maintains a constant CPU temperature no matter what the load is or the environmental conditions are. And that's shown on the graph on the right here, where the factory control is depicted by these 2 lines. There were 5 different workloads run, and the 2 different lines depict 2 different inlet temperatures to the server. And these 2 lines here show our PID controller, which held 75 degrees on the CPU, no matter what the load or the inlet temperature was. So on the server we can monitor many different things, including temperature, power, fan RPM, CPU utilization, and airflow. So these values, most of them are gathered from the OpenIPME interface by a local polling script, which then sends the data to our open source data collection chain, which has been developed at RISE, and uses tools called Zabbix, Kairos, and Grafana. One thing missing from the previous slide was the server fan power. This is not available. So what we did was we profiled the server fans. We interrupted the power line going to the server while the fan was mounted in the server in the chassis, and ran a sweep across all the RPMs to get this relationship. We did this for 2 fans and made an average shown in the graph on the right. So then our question was, what CPU temperature is the best? And there's different things to think about here. For example, that running at higher temperatures might decrease the lifetime of a component. But in our analysis, we looked strictly at the energy efficiency. What CPU temperature is best for energy efficiency? So to do this, we performed a server sweet spot analysis. We ran the server at many different CPU temperatures and at 3 different workloads. We stepped down the CPU temperature in 5-degree steps and waited 2 hours at each step to ensure full thermal stability. We also tried at 3 different inlet temperatures and maintained a 0 pressure drop in all the experiments, meaning all the air provided by the wind tunnel was ingested by the server. This picture here shows a screenshot from our open source tool named Grafana, which was shown earlier, of the experiments in process. The experiments were quite long experiments because of the many different tests performed. So here are the results. The x-axis here shows the different range of CPU temperatures we ran at, and the y-axis is depict power. There are 3 graphs here. The graph at the top is the 8% workload case, the graph in the middle 50%, and at the bottom 75%. So the black line should be read on the left y-axis, and this is the server fan power, which we showed how we calculated earlier. So to hold cooler CPU temperatures, there's more server fan power needed, which is intuitive, that more air has to pass across the heatsink to keep the CPU temperatures cooler. So the solid red line should be read on the right y-axis, and this is the thermal server power. And what you can see here is that as you increase the CPU temperature, the thermal-related losses, including CPU leakage, increase. So there are 2 opposite effects occurring here. So if you add the thermal power plus the fan power, you get the total server power, which is shown by the red dashed line here. And in each load case, there is clearly a minimum. So where does the factory control put us at? There are the dots. The 8% load case is in the minimum, but the 50 and 75 wander away from the minimum. Is there a reason for this? To examine this, we need to look at what happens to the delta T across the server as we increase the CPU temperature. The left axis is now temperature, and you can see that the delta T increases as we increase the CPU temperature in all three workload cases. And we also need to go to the fundamentals of heat transfer. Q equals mCp delta T. If we rearrange this equation a little bit, we see that V dot, or the volumetric airflow, is inversely proportional to the delta T across the server. So if we double the delta T, we have the volumetric airflow. And this is significant because if you think of the facility fans in the fan cube law, having the volumetric airflow needed by the servers will lead to having of the fan speed of the facility fans, which then leads to 1/8 of the fan power being consumed. So to find the holistic sweet spot for these servers, we applied the results from the server sweet spot analysis theoretically to a real data center. This is the RISE OCP lab module, which has 12 racks containing 360 Winterfell servers. The servers are cooled using equal cooling direct fresh air evaporative coolers. Once again, I'll mention the talk coming up in the time slot after this, where this data center will be shown operating in a holistic cooling fashion. So this shows how we calculated the results. We showed earlier how we can calculate V dot for one server using the heat transfer equation. We can multiply this by 360 to get the V dot, or the volumetric airflow, needed for all the servers. We can then go to the system curve on the bottom right here and find the max power for the cooling units and the max airflow for the cooling units. So now, using the fan affinity laws, we have 3 of the 4 variables. So now we can solve for P to the fans, or P facility, which is shown here. So here are the results. The x-axis is the same as before, showing all the different CPU operating temperatures. But now on the left y-axis, we have cooling power, which was shown on the slide before, how we calculated that, and that's the black line. So to maintain cooler CPU temperatures, you need much more cooling power. The red line here, the solid red line, should be read on the right y-axis, is the IT power for all the servers. So if you add the IT power plus the cooling power, you get the total data center power. Once again, for total power, there's clearly a minimum in each case. So where does the facility put us? The factory put us? In the 8% case, it's right in the minimum. In the 50% case, it's drifting away a little bit, and even a little bit farther away in the 75% case. And in this 75% case, we're seeing a potential of 1.5% savings if we would run the CPUs at 65 degrees instead of 77. Once again, I should reiterate that this is a theoretical calculation. The results from the wind tunnel for one server were measured, but then we scaled these up to the entire data center and assumed that all the servers perform as the average of the 3 that were run in the wind tunnel. To make sure that this 1.5% energy savings is possible, the plan in the future is to actually run this experiment on the entire data center on all 360 servers. So the last thing we took a look at was the effect of server inlet temperature on data center efficiency. So we reran this exact analysis at 3 different inlet temperatures in the wind tunnel. We ran it at 29 degrees inlet, 23 degrees inlet, and 17 degrees inlet. And the results are shown in the graph here. The left y-axis is the total data center power. And the x-axis shows the range of CPU temperatures. And when comparing the green, which is 23 degrees, to the blue, which is 17 degrees, if you look at the factory control where the dots are, we were seeing a potential savings of 1.3 to 2%. An important assumption here is that we're assuming the temperature outdoors is cooler than the inlet temperature to the servers, meaning that the cooling units can just ventilate and mix the air. So can we assume this, that we can get air colder than 17 degrees? First, we're going to look at Lulea. This is 2017, all 8,760 hours, plotted on one graph from highest to lowest. You can see here that there are only few hours of the year where the temperature is actually warmer than 17 degrees Celsius. Here we would either have to let the inlet temperature to the servers increase or use evaporative cooling to drop the temperature down. What about a warm summer in Lulea? We have a lot more hours that are problematic, but still most of the year is okay. What if we fly over to San Jose, where this conference was supposed to be held? Oh, things got a lot worse. What if we go down to Los Angeles? Even worse. Let's go the other way up to San Francisco. There we go. That was a good direction to go. Let's keep going all the way out to the coast of Bodega Bay. There it is. That's the place for data centers. But what about wildfires and earthquakes and power? My suggestion is to bring your data centers to northern Sweden, to Luleå. Just make sure to bring your coat. So the conclusions we have here is that we were able to thermally configure these servers using the fan speed control interface, which was very useful. We were able to use the data provided via the IPME interface to perform this research, but we would like to see fan power. The calculation showed that these servers are well designed for direct fresh air cooled data centers at low utilizations. And there's a possibility for improvement at higher utilizations. And we should test this on the real hardware to make sure that this is actually true. And finally, we can save energy by lowering server inlet temperature when using direct fresh air cooling, assuming that it's cold enough outside. Call to action is that we believe that the data from the servers needs to be connected with the cooling systems. And this could be done at the rack level. We could have intelligent racks which gather all the values from the servers and aggregate them, including fan RPM, power, delta T, airflow, and etc. Then it could speak the protocols that the cooling systems want to and connect these two different systems to enable holistic cooling. We could also explore different server configurations depending on what kind of data center the servers will be in. Maybe for a typical crack data center you choose one setting, and for a direct fresh air cooled data center you choose another BIOS setting. And finally, it would be useful to provide the server fan power consumption. Thank you all for listening.
Hello, everybody, and thank you for listening to this presentation. I see that there's no questions that have come up so far, so please send your questions now if you have any. I'd just say a couple things about what we did with the work we did here. Since this presentation, we've continued to work with our wind tunnel, and we've added a Venturi airflow meter to double check with the heat transfer equation. We've added tighter pressure control, including a motorized exhaust damper. So we are planning to continue to work on these results and hopefully publish them somewhere. So keep an eye out for publications in the future related to this work. I also want to say that one thing that was mentioned is that we also want to run this on a large scale on the entire OCP lab module, which we have at RISE there in Lulea. This is possible because of a collaboration that was done with Cooling out of the UK and RISE, where holistic cooling has been implemented on this module. So we should be able to run a sweet spot analysis on a module level. Once again, watch the next talk to see this, the one called BTDC, a practical demonstration of world-class efficiency. So that's a really neat thing to see. So please stay tuned for that, which is held by my colleague, Dr. John Summers. Keep an eye out for publications and new presentations coming in the future related to the same work which we performed. Once again, thank you all for listening, and I hope you enjoy the rest of the show. And I will, since there's no questions that have come in yet, maybe we can give it a little bit of time. Otherwise, I think we just will close this talk and stay tuned for the next one coming up in 11 minutes.